Okay, welcome back, everybody. Sorry I had to start a few minutes late here. Got a technical problem, but got it straightened out. All right, so just a couple quick things. Everybody's on the same page and no surprises. Let me share with you the schedule for the calendar from Canvas. Right, today's the 20th, so obviously you have homework due today. Hope everyone had a good little vacation yesterday, 4-day weekend, I guess, 3-day weekend. Anyway, tomorrow's exam is over chapters 4 through 6. Okay. Same scenario, similar type of questions about same number. Give yourself plenty of time, 75 minutes. It'll be open from, I believe, actually midnight till 11:59. On that Wednesday. So give yourself plenty of time. I go in there and I check to see if you haven't taken it, and I kind of send reminders out. Okay, hey, don't forget about this. So I'll be doing less and less of that as the semester ends, because we're getting close to the end here. You know, you think about it, this is the week of the 19th. We have exam number 2. You know, semester's coming up very quick. Let's look at the next week here. We got July 4th coming up, no class. And then the week of the 17th, right around the corner. Week of the 17th is our finals week, if you will, final week of school. Okay. All right. So much for that. Now, the other aspect is this, Canvas. Canvas is, from my perspective, not a very smart piece of software. For example, if you put an answer in and you inadvertently give it a space, it doesn't understand that space is just a space. And if your answer has, Canvas looks at the number of characters in your answer. So if your answer has, 5 characters, and you inadvertently put a space, it treats that space as the character. So now your answer has 6 characters, and therefore the answer is incorrect. So whenever you look at your answers in Canvas, you know it's correct, but it counted it wrong. Definitely send me an email. I will look at it and for sure give you credit for that. What we've been doing with time is we've been trying to put in any possible way answers could be given so that Canvas can recognize it. In other words, you're going to tell it, give that answer with that space and okay it. And we have done, I mean all the instructors that have worked on these exams, and we have taught Canvas what answers are okay. Well, we're not even near doing that. So check your answers. It's a correct answer. I will give you credit. Which brings me to the point with respect to the electron configuration. Because of Canvas's downfall, I don't say downfalls, but because of Canvas's little quirks about answers, when we ask you to put in an electron configuration, we ask you to put it in a specific format. Simply because that format, if you put that answer in that format, Canvas, and it's correct, it will give you a correct answer. Because in some of the questions, Canvas at one point did not understand superscript. And so we asked that we put, like, for example, let me do a quick example to understand. We have not gone away from the format of how to write electron configuration. No, we haven't. We're just showing you a different way to write electron configuration so that Canvas can grade it properly. Okay, so if you were to just say 1s, 2s, 2p6, for example. So obviously you write a longhand, you got a space in between the numbers, and that's the format that'd be cool. Okay, you can do the same format if subscript is supported. So what we did is we say, okay, Canvas doesn't understand that. It doesn't understand a superscript. as far as an answer. So we say, write it in this format, and we say 1S, and then we put the caret symbol, which is that symbol there, which is the shift, I believe, key 6, shift key 6, and then 2, okay? And that 1S2 looks like that, 1S caret 2, and then we say, don't put a space between there, okay? And then just 2S caret 2, okay? And then finally 2P caret 6. So that's the format we ask you to put it in, simply because that's the way Canvas can understand it, okay? All right. So no, we haven't changed the format. It's still the same format, just in a different manner for Canvas 6, okay? And if you put in this format, and if you inadvertently put a space in there and you get counted wrong, no worries, shoot me an email and tell me what question number, where it's at, and I'll definitely give you credit for it. I have no problem doing that at all whatsoever, okay? All right, any questions about that? All right, let's see. Catherine's trying to get in here. All right. I believe that's all I have. All right, any questions about the chapters? You have an exam coming up for tomorrow? 4 to 6, chapters 4, 5, and 6. Yeah. Okay, well, my plan is to do at least 2 chapters today to get you ready for exam number 3. And then if, because they're fairly short, we can probably knock them out today. If not, definitely we'll finish with the next group of chapters on Thursday for the following exam. Okay, and this one deals with nomenclature. Now, remember nomenclature with respect to what aid, what additional tool you have. Nomenclature is just a fancy name for name that compound. We're gonna start learning about how to name the compounds, and then eventually get to the point from given the name, write the formula, or given the formula, write the name. Okay, and so a quick reminder is that on Canvas itself, we have, make sure I get, let me get to Canvas. Okay, on the far left, there's an additional aid for you to help you with this nomenclature, is a StudyMate. Okay, I did talk about this earlier semester. Let me go through it again. StudyMate is a program. Okay, I don't know if it's my, today we're going to be doing chapter 8. Somebody asked a question. Today's chapter 8. Something's going on here. I don't know if it's Canvas acting up, but I've been having this trouble all morning where I'm trying to access some of the modules in Canvas and it's just telling me to wait. And my internet is okay, so anyway, just a quick reminder then, and since I can't get to it right now. In Canvas itself, there is a StudyMate icon. Now I finally let me somewhat. Here it goes, okay? And there is a what nomenclature practice. This is a program that built into StudyMate that you can utilize actually not only for this class, but you can utilize it for your other classes because you can make projects here for yourself to help it out. And what I've done is I uploaded, I forget, about 143 flashcards or formulas and names to help you. So what this does is you can, if you select the flashcard, you're given the formula, name, nitrogen triiodine, and then from that information, write the formula, okay? So once you do that, then you flip the card and then the formula is given to you. So nitrogen triiodine. Now keep in mind that again, this one doesn't support subscripts. So that 3 really is a subscript if you were to write that out correctly by hand, okay? But StudMate doesn't support it. Okay, or you can go to the next card. Here you're given chromium Roman number 3 hydroxide, and from that information, come up with the formula. So you can also, you want to be to the point where you go from formula to name or vice versa, okay? You can use the flashcard or you can use the matching. I wouldn't use the other choices because the other choices, you're welcome to go in there and see and look at them. But what happens is some of those other choices don't understand what to do with parentheses and subscripts and so forth. So it kind of gives you the wrong information. But matching, a check matching a flashcard is pretty straightforward. So in the matching is you're given the name dinitrogen monoxide, and then from that you go around and you find the formula. Dinitrogen meaning 2 nitrogens, monoxide meaning 1 oxygen. So the formula have 2 nitrogens and 1 oxygen, which that would be the case right there. Okay. So again, this is the NAED for you. And you might say, well, why do I need this? And you will need this because you have an exam called the nomenclature exam, which no one's attempted that yet, but that's okay. But I would suggest starting to doing it right here in the nomenclature exam. It's a series of 20 questions where you're given either the formula or the name, and you're supposed to answer one or the other, okay? And it is required that you get at least an 80%, so 16 out of the 20 questions correct. And then that's a passing grade. Anything less than 80% as per Scottsdale as the chemistry department's policy, it gets reset back to 0, okay? That part is worth 10% of your overall grade. It may or may not affect your overall grade, but if you're on the border, it can, okay? And if you're on the border where you're maybe on the B and you're trying to get up to the A, that 10% can prevent you from jumping over to. And vice versa, it can, if you don't, it can drop you, okay? So now, right now, everybody has a 0 in that grade. What I'm going to do here, not this week, but maybe the following week, is I'm going to put a 0 as a grade. Before you get all crazy, I do this for a reason that I'm explaining. In the past, I made that exam not due until like the last day of school, okay? And, sometimes students being students, they put it off. I would remind them, you got to get this done, but I guess they figured, oh, it's not due to the last day of school. I'll worry about it then. Okay. Well, last day of school came. Everything's turned in. They attempted it. They did not make the 80%. It goes back to 0. And their grade, where they thought they were, gets dropped. They were doing a B, maybe got dropped to a C. They were doing a C, got dropped to a D. Okay. And so then they only had a few hours to work on it and try to get additional 10s because the day it was due at midnight, everything shuts down. Okay. So they were scrambling to try to get that up. And once it shuts down, that's the end. So what I started to do is about halfway through the semester, I manually went in there and placed a 0. So you can get a true picture of what your grade is when that's a 0, okay? I'm going to do that again So you have plenty of time from now until the end of the semester to do attempts. Why? Because you have unlimited attempts. Unlimited attempts to do this particular nomenclature exam. And it will keep the highest score. And once you hit the 80%, you're happy at that point, just keep it, you're done. Once you take it, I go in there and I check your answers because again, Canvas doesn't quite understand some of the answers. I go in there and double check your answers, and I a lot of times I give you correct, give you credit for some of your answers. Okay, depending on your answer. And sometimes, even though you might think you didn't make the 80%, once I run through it, it kicks you up to the 80, you're good to go. Right. Next question is, okay, if I'm at 80%, can I continue to try and push it up to wherever? Yes, you can. Even if you pass it at 80 and you want to get higher, just keep trying if you want, or you can stop at the 80. Okay. So, and next week, like I said, don't be surprised that the grades right now that you have get dropped. Keep that in mind, that it gets dropped, because Canvas, what Canvas does is it only gives you a grade, overall grade for what's been graded. And so there's things that you haven't done yet that you obviously you haven't been graded. So not until you're graded that grade is incorporated into your overall. And so the nomenclature is not in your overall grade, because it hasn't, unless you attempt it. If you attempted it, then yes, it gets incorporated. And a lot of people, like I said, haven't attempted it yet. So I will, if you haven't attempted it, I will put a grade in there, and everybody will get a 0. Okay, so that's where you're starting off as, to give you, so you have a better idea where your grade truly is. If the semester ended that day, that would be your grade. And it will further give you an idea of the impact that 10% may do. Plus, you have plenty of time from that point to the end of the semester to finish that nomenclature. Okay. All right. Any questions about that? No? All right. Well, that being the case, let's jump into chapter 8. And let's talk about nomenclature. Okay. Nomenclature is just, like I said, a fancy word for name that compound, the name of a compound. All right, let's talk about the names of the atoms, which we have been already. We, keep in mind what we're doing now, or have been doing. We talked about the atoms, the individual atoms, okay, and we've gotten asked to learn at least the names of the first 20, and then we had a series of others to learn. We're going to be adding more as we go. Are we going to have to deal with all 118? No, not at all. We're not going to do that. We're telling you which ones we'll be using, okay? We have the atoms themselves. Then we learned about the electrons and valence electrons, and how metals want to lose electrons and how non-metals want to gain electrons, because they want to get to that magical 8 number with respect to the number of valence electrons on the outermost shell. Those created ions. So from the elements, we created ions. And from the ions, we start putting them together, the positive and the negatives, to make compounds. And once we start putting those together, they start naming them, okay? Naming them. So neutral atoms, we like sodium is called sodium atom. And Ne, obviously, the eon. So we talked about learning the first 20, name-wise and formulas, okay? And then we added barium, cobalt, iodine, copper, iron, lead, mercury, silver, gold, zinc, stannous, 2 names for stannous, SN. In fact, this morning, if you brush your teeth with fluorinated toothpaste, you either brush it with maybe sodium fluoride, if you look at the label, or you may even have stannous fluoride, and that's what SN. Another name for stannous, SN, is tin, TIN. So you were brushing your teeth with tin fluoride. So you can call it stannous or tin, T-I-N. Strontium, nickel, bromine, chrome, manganese, as not to be confused with magnesium, which is Mg, okay, and then cadmium. Those are the ones that we added, and we're probably going to add just a few more, okay. Now, with respect to ionic compounds, we talked about this. What formulates an ionic compound is the combination of a metal, which is a cation, okay, has a positive charge, and a nonmetal, which is an anion, okay? That when those combinations come together, the one aspect about these compounds is that it is the coming together of a full positive charge and a full negative charge. And they come together with the electrostatic attraction. They're not making a bond. We call it a bond, but they're coming together like two magnets coming together, okay? There's nothing sharing in between them. They're being attracted to each other because of their respective charge. Now, when we make these compounds, expect a negative and a positive coming together. Don't expect two positives to come together because positives repel. Nor don't expect two negatives to come together because negatives repel. It's only a negative and a positive. A covalent compound, also known as a molecular compound, consists of nonmetals only. Okay, so you might want to refresh your memory as far as using the periodic table to determine who's a metal and who's a nonmetal. And recall that the stair steps is what you look at. The stair steps, the elements on the stair step are metalloids. Anything to the left of the stair step are metals, except hydrogen, okay, which is in the far left in group 1A, and everything to the right of the stair step are nonmetals. Okay? So we have a combination of nonmetals only, two different nonmetals. We have a covalent compound, aka molecular compound. In this scenario, with covalent compounds, there's actually a sharing of electrons when they come together to form an actual true bond. And within covalent compounds, we have two types of sharing. We have an equal sharing, which makes what we call a non-polar bond. And then if there's unequal sharing, we have a polar bond, okay? You have an unequal sharing. When you have an equal sharing, we back it up. When you have an equal sharing, normally what's happening is you have two elements that are the same. So all the diatomic compounds like hydrogen, oxygen, there's two atoms of the same, there's equal sharing, okay? And we have a non-polar bond. The other example is a carbon-hydrogen bond, which is basically equal sharing because the electronegativity of carbon and hydrogen is essentially the same. When you have two different elements come together, okay, you have let me write this down here. And so if I have the example of an A bonded to an A, we have what we call a non-polar bond. Non-polar bond because there's equal sharing going on here. Also in this category is a carbon-hydrogen bond. We consider that as a non-polar bond. When you have the scenario where you have two different elements, then we have a polar bond. Okay, polar bond, because one of these elements, A or B, has a higher electronegativity. Remember, electronegativity is the affinity for that element to pull electrons onto itself. And if B has a higher electronegativity, then it's going to pull the electrons onto itself much greater than A, which results in this having a partial negative area and A having a partial positive area, which results in a dipole. Okay, dipole meaning two poles. Like the Earth, there's two poles, the North Pole and the South Pole. We have a dipole on the Earth. Another example is a battery. You've got two poles. You got a positive pole and a negative. Okay. Well, when the electronegativity of one of these atoms is greater than the other, we result in a dipole, which then results in a polar bond. Polar bond. Okay. As compared to the AA scenario where we end up with a non-polar bond. That itself gives you different properties in the molecule as far as solubility and some other things that we're going to learn about. So we have to be able to identify whether we've got a polar bond and a non-polar bond. And we're gonna use that property quite a bit. Okay, so those are covalent compounds. One second. Okay. Now, we have monoatomic ions. So the elements that have lost or gained electrons, they're just the elements themselves. So we have the sodium that became the sodium ion. It's a sodium cation, flow with a plus charge because it lost one valence electron. In this example, we have chlorine that went to chloride because it picked up one electron. By picking up one electron, remember the chloride's in group 7A. It only needs one electron to get that octet, okay? And we also change the name. It is the nonmetals that when they become ions, that we change the name. The metals themselves remain the name. We just have to designate either as sodium ion or sodium atom. Okay, so chlorine went to chloride. Okay, but we also have what are called polyatomic ions, where we got two or more atoms have come together, and we're going to learn that the ones that come together are basically all nonmetals, but overall, as a unit, they have an overall charge. Like the PO4 -3, that's called the phosphate. Now, I direct you to the periodic table right here. And furthermore, if you look in the bottom left corner of the periodic table, you have a table here called most common polyatomic ions. Now, this is by no means an exhaustive list of all the polyatomic ions out there. There's many, many more. But for us at K130, we're going to focus on these, okay? You'll see that it's either going to be a positive or negative, but there's only one positive polyatomic ion. That's the ammonium. Let me see if I can zoom this up a little bit more. Here we go. Okay, so you can see the NH4 plus is called the ammonium. That is the name for that polyatomic ion. We have a number of different other ones. We have the NO3 negative. That's called nitrate. And then -1 oxygen, where we got the NO2 negative, is called the nitrite. Okay. We also have the sulfate, which is sulfur bonded to 4 oxygens. Now, this could be a little bit confusing. Let's work on this for a second. Let's look on the sulfur, for example, and we'll go from there. Now, let me clear this up. And, we have sulfur. Okay. Now, when sulfur becomes the anion, because it's in group 6, it will pick up 2 electrons. We change the name to sulfide. Okay. In fact, you'll see the IDE when we look at all the nonmetals and they become their respective anion. Nitrogen becomes nitride, oxygen becomes oxide. You can tell by the prefix what element we're talking about, but more importantly also is the IDE tells you that we're talking about that element by itself. So the sulf part says we're dealing with sulfur, okay? And the IDE tells us it's the -2, it's the single element itself. Because we have some polyatomic ions that contain sulfur, and you'll notice that what is attached to all these are oxygen. Specifically, in this case, we have 4 oxygen, okay, bonded to the sulfur. And it has an overall charge of a -2. This species is called sulfate, okay, ATE. Now, if we subtract a oxygen, and we're going to go through this, these polyatomic ions and how we can name them. I have a couple of slides for you and some PDFs describing it. If we take one oxygen away, now that becomes sulfite. See, so note the ending. Sulfur is the element. Sulfide is the anion of sulfur, okay, with its charge, -2. Sulfate, 8 part, and ite should tell you, okay, we're dealing with sulfur, but we also are dealing with oxygen bonded to that sulfur. Okay, so there's 3 examples there of the sulfur and their respective names. Now, all these polyatomic ions are units. We don't separate them. If we ever need more than one of these units, these polyatomic ions, we put parentheses around the whole thing. So if I need, say, 3 of the sulfates, for whatever reason, I put parentheses around it, and then I put a subscript X here, which could be, do I need 2, do I need 3, do I need whatever number I need, okay? And that is true for all of these polyatomic ions. Whenever you need more than one, you need to put a parentheses around it and put a subscript to with the number of what you need. Now, the number that you're going to need depends on, normally you're going to tie it up with the cation. And sometimes you only need 1 of these, and then you don't need a parenthesis. But if you need more than 2, then you put a parentheses, and then enough of them to counter the positive that's coming from the metal, okay? So point number 1, you need more than 1 of these polyatomic ions, you use parentheses in the subscript. Don't change the formula. So this is what I mean. Let's say, for example, I need 2 sulfates. So like I explained earlier, I would put sulfates, and then, oh, that's a 4. It's supposed to be a 4. And then I put a subscript 2 here, okay? Showing that I need 2 of them for whatever reason. Don't do this. Don't make this S2O8. Okay, I have no idea what that is. That is not 2 sulfates. In other words, don't change the subscripts of the polyatomic ions. In fact, don't change the subscript once you put them together of any compound. Okay, so that's point number 1. Point number 2 is every one of these polyatomic ions has their specific name. So this one is called sulfate. This one is called sulfite. We got the cyanide. Oh, learn this guy quite a bit. We're going to use him quite a bit next chapter, the hydroxide. Okay, that is the name for that polyatomic ion. This one you might be familiar with, sodium bicarbonate, right here. Good old baking soda. Okay, they have their own specific name. Don't change the name. Come on. It's a polyatomic ion. Now, I've been using the term charge. Okay, so let's say sodium lost an electron. It has a charge of a +1. Okay. Oxygen gained an electron, 2 electrons, now has a +2, -2 charge. Okay. And when we talk about charge, that's okay. It's very descriptive for ionic compounds because they have a full charge. But when we talk about covalent compounds, we're not talking about a charge because they're bonded together and they're not separated. Okay. So what we use for a description of their respective charge, because ionic compounds have a partial charge, okay, and ionic compounds have a full charge. You get that? Let me get that straight. Whereas covalent compounds have a partial charge. Okay? And so we can't correlate the two with respect to what kind of charge. So we use the term oxidation state. Okay. And so if all the elements have a 0 oxidation state, and that's because they have an equal number of protons and equal number of electrons. Sodium, for example, when it loses an electron, its new oxidation state is a +1. Okay. And if they gain an electron, like they say chlorine becomes chloride, now its new oxidation state is a -1. Okay. Now, some elements have a fixed charge. So there's only one possibility. I'm going to give you some examples where other elements have a variable charge. For example, copper can exist either as a +1 or a +2. Another example is iron. Iron can exist as a +2 or a +3. So it becomes a little bit ambiguous. And the question is, how do we distinguish between a copper +2 and a copper +1 or any of the other ones? Because we're going to learn that the group B, the transition metals, can have multiple different oxidation states / charges. There are 16 elements that have an oxidation state that occurs 100% of the time. And you need to be familiar with that because that means that you don't have to do something to them when we name them. I put these encircled them in the red box, okay? Now, group 1 elements, we're starting with lithium in group 1A, okay? Lithium on down. Everybody there, remember, has a 1 valence electron, okay? 1 valence electron. So, and they're metals, so they're going to lose that 1 electron and end up with a +1 charge, okay? Everyone agree on that? The second group in, 2A, they have 2 valence electrons. And so they would have a +2 charge 100% of the time. And that's what I got written up here in red. +1 and +2 for the group 1A. I'm not including hydrogen here, though hydrogen can have a +1, which we're going to learn about that next chapter, because I'm just talking about the metals. But hydrogen can also have a negative charge. So we're not gonna put this on this list. So group 1, we got 1, 2, 3, 4, 5, 6. We got 12 elements from the group 1 and the group 2 that 100% of the time what their oxidation number is when the atom becomes an element. Okay, so that is 12 of them. We're going to add 4 more to this list, and I circled them over here on the far right. On the far right, you have good old Al. Okay, Al, or AKA aluminum, will always have a +3. Okay, Zn, which is zinc, will always have a +2. And it'll keep going to Ag, not to be confused with Au, because Au is gold, but Ag is silver. Ag will always have a +1. And then move it to the right, Cd, always have a +2. Okay, so that means that, so if you look at the way that it comes, if you start aluminum, you can draw an arrow down this direction, and then from here go that direction, like a little wedge. So there's 4 plus the 12. That gives you 16 metals that you know the oxidation state 100% of the time. What that means is that everybody else, all the other metals, will have a variable charge. Okay? All the other metals will have a variable charge. And what we do to distinguish them, like for example, you have copper 2 and copper 1. The question is, how do we determine which one is which? Well, what happens is we utilize Roman numerals. So if we're going to describe copper 1, okay, we would say, if we write it, let me write this thing down. We would say copper, parentheses, Roman numeral 1. What that tells us is we are working with copper with a +1 charge, okay? And it could be +2. Iron, for example, exists in the state as either a +2 or a +3, okay? And like I said, all these other metals can have a variable oxidation state. When we need to describe those, we have to be specific, and we have to write their name longhand and then put in parentheses the Roman numerals to describe what oxidation state. Now, let me share with you something, because I learned that I guess Roman numerals aren't taught much anymore. Okay, so I should have talked about this earlier. So Roman numeral letter I, uppercase I, as compared to the little I like this, you know, we use the uppercase. So, and then we got Roman numeral 2, Roman numeral 3, Roman numeral 4 is written with I in front of V. V represents 5, okay? And if I put 1 I in front of V, we subtract 1 from 5 to give you 4. So this is 1, 2, 3, 4, and this is 5. If we put an I after the V, that is 6. And we had another I, we got 7. And then V triple I, we got 8. And if we add an I, X is 10. So if we put that I in front of X, that's 9. And then X itself is 10. Okay, those are the Roman numerals, which, you know, we have been using. This is group 8 up here, V8, V3, triple I, A. Okay, those are the Roman numerals. And so when we use them in the name in parentheses, that is telling us what the charge is. So metal, parentheses, I1, Roman numeral I, capitalized, tells us we're dealing with the metal with a +1 charge. If it's metal, parentheses, IV, we're dealing with that metal with a +4 charge, okay? That's how that works. All right, so with respect to nomenclature, with respect to naming them, okay, when you're dealing with the sweet 16 here, as I call them, you don't need Roman numerals, because those are exact oxidation numbers. And it is known that aluminum will always have a +3, so there's no reason to put Roman numerals for aluminum, Roman numeral 3. It's just strictly aluminum, okay? Sodium, lithium, potassium always have a +1. So they would always have no name. They just give the name, no Roman numerals, okay? So don't put Roman numerals on these 16 metals, but do that with respect to all the other ones. Now you may ask yourself, well, which metal, what oxidation number do we use for the ones we don't know? Well, Good question. Okay. You will always know the oxidation state of either the cation or the anion. And remember, when we put them together, they're going to equal 0. Okay. So you can solve for what the oxidation number is on the other. So let's talk about the anion part. The anion part, for example, group 5. These guys will always have a -3 charge. So nitrogen becomes nitride, phosphide, etc. Next group will always have a -2, and next group always have a -1. Okay. So if, for example, you had a metal X and it was bonded to oxygen, 2 of them, could I calculate what the oxidation state for X be? Okay, let me try that again. I don't know what X is. It's some metal. It's some hypothetical metal here. And the question is, what is the oxidation state for X? Can I calculate that when it's bonded to 2 oxygens? Can I calculate what the oxidation state of X would be? Okay, keeping in mind that when I put these together, they have to equal 0. Okay, well, the question is, what is the oxidation state of oxygen? Right here. When it becomes an anion, what is it? What is oxygen? What is the oxidation state of oxygen? Be it an ionic compound or covalent compound. What is its charge?
-2.
You got it, -2. And if there's 4 of them, so what's my total negative?
4.
Exactly. So it's -4, and then it's X minus -4 equals 0. So what must X be?
4 positive.
You got it. So X has to be a +4. Okay, and that is the oxidation state of X when it's bonded with 2 oxygens. And if it was bonded with 1 oxygen, what do you think its oxidation state would be now? If it was XO versus XCO.
0.
Not quite. Again, what does each oxygen always have? +2. There you go, Catherine, got it. Because again, just like we did down here for the first one, we know that each oxygen has a -2, and there's 2 of them, so the total is a -4. Under this state, there's only 1 oxygen, so that's a -2. And that has to equal 0. So that means that X bonded here must be a +2. +2 minus 2 equals 0. Okay, so that's an example of the different oxidation states of X. Let's do a specific example. And the exercise here is to show you that you can calculate what the oxidation state is of one metal. Let me restate the comment. You will always be able to determine the oxidation state of one or the other. Okay, let's look at two common compounds, carbon monoxide and carbon dioxide. Okay, now granted, they are not ionic compounds, and that's okay, they're covalent compounds, but you can still calculate the oxidation state of carbon and oxygen. Okay, because oxygen here will have the same oxidation state we just described. What do we say oxygen always has? It always has a -2. Okay, and it is bonded to carbon. Carbon must be a +2. So the oxidation state of carbon, when it's bonded to one oxygen, must be A+2 because I gotta have enough oxidation numbers, positive and negative, to equal 0. Okay. Over here, same scenario. This is true for any element. Everything has to equal to 0. Oxygen has a -2 for each one. We have a -4 total for all the oxygens. That implies that carbon in this state must be A+2. And that's the case when it's bonded with two oxygens. Okay, so we can calculate one or the other, knowing what the oxidation state is of one or the other. Let me give an example of, let's say, magnesium X. Okay, magnesium X. What must be the oxidation state of the element X? X is some hypothetical element. Okay. What do we know about magnesium and its oxidation state? See, nothing's
Positive.
changed. It's a positive what?
+2.
You got it. So this is a +2. We know, like we've done before, that we put them together, they must equal to 0. So what must X be if magnesium is a +2? It's got to be negative, obviously, but what's the magnitude of negative?
2.
You got it. So under this state, notice how over here we knew the anion, the oxidation state of the anion, and over here we know the oxidation state of the cation, which allow us to calculate the oxidation state of the partner, okay? All right, so it's got to be a +2. Okay, let's do this one here real quick. All right, we have copper oxide. Okay, first question to ask yourself, is copper one of the 16?
No.
No, that means that not being one of the 16, that its oxidation state is variable. So we don't know what it is. We need to figure it out. Okay. Again, we know that oxygen is a -2. So what must copper be? What is the oxidation state of copper when it's bonded to one oxygen?
2.
Exactly. It has to be 2, +2. So that means that if we were going to write the name out, we would say copper, Roman numeral 2 in parentheses, oxide. And that is the name of copper 2 oxide. Here's the formula. Okay. What if it was copper subscript O? Can we determine what the oxidation state is of copper? Sure we can. Okay, just a little bit more algebra, but it's the same. So we have here, we always know that everything must equal to 0. We know that oxygen has a -2, and we know that copper, there's 2 coppers. So don't we have an algebraic equation, Cu - 2 = 0? Don't we need to solve for copper? What do you guys think the oxidation is of copper bonded in this state? Let's solve for it. So we got Cu, 2Cu equals +2, right? I put a -2 on the left, +2 on the left, +2 on the right. Okay. Then I divide through by 2. So copper is equal to +1. which makes sense. That means that I got two coppers here, and each one is a +1 to counter the -2 of the oxygen. Okay. Now to name it, it would be both, in both cases, this one and this one, they both have the parent name of copper oxide. Where they differ is the bottom one has a Roman numeral 1, the top one has a Roman numeral 2. Those are two complete different coppers, two complete different chemicals. Okay. Copper 1 is, copper, one of them is a real nice, beautiful looking blue color, and the other one is more of a greenish color. Yeah. And so totally different, even though they're both copper, the difference between one electron makes a big factor. Okay. So that is what we do with respect to those metals that are not in these circles here. Okay. Because the ones that are in the circles have a constant oxidation number. We don't use Roman numerals for them. Everybody else, all the other metals have Roman numerals. You have to use Roman numerals. And most of the time, unless it's given to you, you have to calculate, figure out what is that oxidation state for that metal. Okay, so I would take my periodic table and just mark them. That's what I did here, mark them. Yeah, and so I can remember that the sweet 16, no Roman numerals. All right. We talked about this at length, cations, metals. When they lose electrons, we talked at this at length. These is metals in their respective group 1, group 2A, +1, +2. Aluminum always has a +3. Then we added zinc and cadmium with a +2 and silver with a +1. Those are the 16. All the other metals, their oxidation state can vary from a +1 all the way to a +9. Depends on the metal itself. So, and therefore, to distinguish them, it used to be like, for example, copper. The old naming was cupric and cuprous, the IC-ic and the us. But that was quite ambiguous, and it could be very confusing which one we're talking about. And so the world community, there's an organization called IUPAC, which is an international community, whose function is to set the precedents or set the naming of a compound. You know, they have certain rules of how a compound is named. And so therefore, all the chemicals around the world are consistent. And so when I talk about a specific compound here and give it its name, the scientist on the other side of the world understands what compound I'm using. You know, it's really interesting. I was in the lab one time, as a little side note here. There was a scientist from Japan, one from Lebanon, myself, and another one I believe was from Africa. Yeah, he was from Africa. Now, the common language was English, broken English, but English either way. So the Japanese scientist spoke English. It was not the best, and the Lebanese, he did okay. But we were trying to make a particular compound, and so we're drawing the structures on the blackboard. Yeah, that's the day of the blackboard with the chalk. And we sat there and we figured out how we're going to do this. And everybody took the turn on the board and writing all the chemical steps and so forth and chemical reactions. But the point is we all wrote it on the board and we understood exactly what we were going to do. You know, it was like, you know, I don't want to say that chemistry is a language, but in that scenario, it was. We were able to communicate and not be able to use our other person's language to be more descriptive. We just drew everything on the board. So it can be a somewhat of a language. All right, so going back to here, there's other metals that have an oxidation state that vary from a +1 to +9. To distinguish them, we have to use Roman numerals, okay? To make sure that there's no question that we understand what the charge is. And the thing to also remember is the following. Clear this up. That the number of cations plus the number of anions must equal 0 when we put these together and make the compounds, okay? When we put them together. So they must equal 0. Now that's in 99% of the time, that is, the whole thing adds to 0. But it's feasible that the overall compound may not be equal to 0. And so to kind of give you an additional equation that encompasses everybody, okay, is simply to say that the number of cations plus the number of anions. And when I say cations and anions, I'm using the term loosely because, yes, we have ionic compounds with a full positive, but we also have covalent compounds with a partial positive. And I'm calling those cations too, but it'd be called partial cations if you want. So those would be equal to the charge of the molecule. Okay, let me give for example. Earlier, we used carbon dioxide. Okay, and so I knew that carbon plus a -4 equals 0. Okay, because the overall charge of carbon dioxide is 0. There's no charge up here. But we just talked about polyatomic ions, and those guys have charges. And so if I say, let's look at the oxidation state of sulfur in this state, can we calculate it? And the answer is yes. Okay, so we know we got sulfur. And what is the oxidation state of the oxides? Be it covalent, be it ionic. What is an oxide? What is its oxidation state all the time? What group is oxygen in? Pardon me?
Covalent?
Well, yeah, covalent, but what is its oxidation number, its oxidation state? It's a negative or a positive value? Which one is it?
-2.
-2, exactly. All the time, remember that oxygen will always be a -2, be in ionic or covalent. Here it's a -2 in carbon dioxide. In sodium oxide, it is also -2, always will be, okay? So here we have oxygen being a -2, and how many do we have here? There's 4 of them. So we have a total of -8, and that molecule is equal to a -2 overall, it has an overall charge, okay? So now I solve for sulfur. Sulfur is equal to 8 minus 2. Sulfur is equal to a +6, okay? So under these conditions, the sulfate has an oxidation number of a +6, okay? So notice how I used the first equation was given to you right here, but then I took the equation, I just expanded it a little bit and just said that is the charge of the molecule. A lot of times a molecule has a 0 charge, but it's possible that you can have a polyatomic ion where the charge overall of the molecule is not a 0. In this case, it's a -2, okay? And we know the oxygen is always equal -2, the oxidation state for all the oxygens. And there's 4 of them, so I got a total of -8. So it's sulfur minus 8 is equal to a -2. I'm solving for sulfur. Simply move the -8 over to the right side. It turns out that sulfur has an oxidation state of a +6 when it's bonded to as a sulfate polyatomic ion. Okay, so I think the second equation kind of expands the choices that you can use to calculate oxidation numbers. And there are questions that they ask you, like I just gave you now, specifically for sulfate, where they state, okay, the ion has a charge of this. What is the oxidation state of a hypothetical cation? Okay, and you can use the second equation. Like you use the second equation all the time, yeah, no problem. Right? Does that kind of make sense? Okay, hopefully it does. All right, so let's go back to the chapter here. Okay, we know about the anions. They gain these. The elements have gain electrons. Those are the nonmetals. So group 5A usually has a -3, -2, -1 respectively. And of course, the noble gases, they're not gonna do anything. Okay, you just think of them as just elements. You just sit there do nothing because the octet will fill. Okay, we're going to begin by learning the formulas and the names for ionic compounds. Okay. Remember that ionic compounds are made up of ions and have a full charge. The other thing to remember is that we don't use prefixes if we have more than one ion of any one. For ionic compounds, no prefixes, okay? No prefixes. And the sum of the charges, like I just explained earlier, must equal 0, okay? And that's when we're talking about neutral compounds. If you don't have a neutral compound, then they're equal to whatever the charge is of the compound. And we have polyatomic ions. These things, be familiar with them. The thing to remember about them is we keep them together. They are a unit. And if we want more of them, they have a unit with their own specific charge of -1 to a -3. And if we need more than one of that unit, then we put a parenthesis around it and put a subscript, the number of how many of those units we need, okay? As we stated, as we put them together, they must equal neutral, meaning that the number of each, the cation and anions may equal 0. So you may be asked the question is okay, combine sodium and nitrogen, okay? Well, what we got to do first is convert them into ions. And we know that sodium is in group 1A, and when it becomes ionic, it will have a +1 charge, okay? Nitrogen is in a group 5A, and it's a nonmetal, so it will gain electrons, specifically 3 electrons, because it's in group 5. It needs 3 to give us that magical 8 number. Okay, and in gaining 3 electrons, now has 3 extra electrons, so its new net charge is a -3. Now, to put these together to write a formula, we need to write them such that we have enough positives to cancel the negatives. So we're going to need 3 sodium ions to cancel the -3 of the nitride. Okay, so first things first, they gave us the elements. From the elements, we converted those, determined what the ions were. Okay, and then once we know the ions, we then determine how many of each we need to put together. And that number in front of sodium becomes a subscript for sodium. So the formula for this would be Na subscript 3N. Its name would be sodium nitride, not nitrogen, okay? It's no longer nitrogen. It is now the ion of nitrogen. Nitrogen is the element, okay? And when it becomes ionic, it becomes nitride. So there's the formula. Okay. Similar thing, they give you the formulas, right? They're not giving you the ions, but they're just telling you, okay, here's the elements, write the formula if we were to put these together. Well, first things first, we write the ions. We have sodium plus, like we just did, and sulfur becomes sulfide as a -2. It tells me we need 2 sodiums ions for every sulfide. Okay, so its formula is Na2S, sodium sulfide. Okay, no longer sodium sulfur because now it's ionic. Okay, magnesium has a +2, and oxygen, like we just talked about, like sulfur, always has a -2. In this scenario, I can put one of each, one magnesium for every one oxide, because I got a +2 and a -2. I can put them together in a 1-to-1 ratio. There's the formula. Potassium, all right. You guys break it down for me. What is the oxidation state of potassium?
One positive,
+1, that is correct. Okay. Now, what about phosphorus?
three negative,
-3, exactly. Okay, so from the elements, I got to convert them into the ions. Once I know the ions, now I know how many of each I need. So I need 3 potassium to balance out the -3 of the phosphide. Okay, so its formula now becomes K subscript 3 P. Now, if you're in Canvas, for example, and it doesn't allow you to do subscript, sometimes it does, sometimes it doesn't. If you were to write it K, simply K3, with no subscript, that will be okay. Okay, let me reemphasize that. If you're in Canvas and you have to write in that answer, the answer doesn't support subscript, because he'll tell you there, use the letter T square or something like that, then leaving it not subscript, it's good to go. You're good to go. Okay. All right. So far, so good. And its name is potassium phosphide. Notice that I have not used Roman numerals. Sodium sulfide, magnesium oxide, potassium phosphide. Why haven't I used Roman numerals? To name these compounds.
not one of the 16.
You got it. The fact that they're not one of the 16, they have an exact oxidation state, we don't have to use Roman numerals, because sodium will always be a +1, magnesium will always be a +2, and potassium will always be a +1. Okay, good. It would be incorrect actually to use Roman numerals. If you were to say sodium Roman numeral 1 sulfide, then that would be incorrect, because by convention and by the rules, you don't need Roman numerals for these 16. Second of all, you wouldn't use prefixes. So it would not be disodium sulfide. So you got 2 sodiums up there for the first one. It's simply sodium sulfide. Okay. Unlike covalent compounds where you use prefixes. Because, for example, there, CO2 is carbon dioxide. Okay. Totally different. No prefixes for ionic compounds, prefixes for covalent compounds. All right, this one's a little more challenging, but we can make this happen. All right, we got calcium here with a +2. Everybody agree on that? Okay. Then we got nitrogen becomes nitride, which has a -3. Okay, now we have two dissimilar numbers. We got a +2 and a -3. How do we put them together so that the charges cancel out? What can we do? Any suggestions?
Add one more to chromate.
To where we don't have chromate though. And which one? We have calcium. This is
Oh,
C.
calcium. Oh, wait.
Okay,
Calcium.
if I add 1, that makes a +4. I got a -3. So that won't work. But okay, let me give you guys a hint. Go ahead. You had another suggestion? See, the other 3, no problem, straightforward. I had 3 of E, 3 of potassium, 2 of sodium, put them together and good to go. But over here, I got a dissimilar number. I got a +2 and a -3. Question is how I put enough of each. Well, think about this. What do you do when you say, I want to add 1/3 plus, say, 1/4? How do I add those two fractions together? Without going to Google. Multiply both sides, Rachel, with what? How do I get the 1/3 and 1/4? Yeah.
Times 3 by 4 and 4 by 3.
Okay, what is it you just did? What did you do?
I'm not sure what it's called.
Yeah, you look for a common factor, right?
Common factor, yes.
Okay, and what's common between the 3 and the 4?
12.
You got it. So our common number is over here. Our common factor is 12. So I change the 1/3 to 12 and the 1/4 to 12. Same technique over here. I got two dissimilar numbers, so I need to find a common factor on both sides. What would be the common number between the 2 and the 3?
6.
You got it. So I need to add enough. I would need 3 +2s and 2 -2s. So here now I got 3 +2s, that's a +6, and 2 -3s, that's a -6, and that equals 0. So that number I just put in is the subscript for each particular species. So it becomes calcium, subscript 3, nitride, subscript 2. Okay? So I found a common number between the two, so I can make sure that I write the right number in the subscript. All right, so I end up with that particular formula of Ca3 and 2. Now, as a little hint to help you out, if you really think about it, if you don't see it, don't use it. But what happens is this. The subscript of the anion is originally the charge of the cation. You see that? And the subscript of the cation is the charge of the anion. Okay, that's a nice little tool that you can utilize to help you. But if you don't see that, don't do it until you're comfortable. Right now, find a common number and just proceed with the formula. So that is the formula for, again, calcium nitride. Okay. Now, at this point, you should be building up your library, because even though sodium is bonded to sulfur, there's no reason why you couldn't say sodium oxide, sodium phosphide, sodium nitride, magnesium sulfide, magnesium phosphide, etc., magnesium nitride. Mix and match. You notice you can mix and match all you want, okay? There's a bunch of metals, there's a bunch of non-metals. You can do a mix and match, and your database with the chemicals that you have is slowly increasing. Slowly increase. You probably up to maybe 100 compounds right now. But you should eventually, no reason why you couldn't be up to at least 1,000 or more as far as your database is concerned. And it's just a matter of mixing the cation, the metals, with the non-metals, back and forth, okay? All right. We have Al, which is aluminum. Okay, so we know that aluminum has a +3, and the chlorides have a -1, okay, because they're in group 7. And so that means I need 3 chlorides for every aluminum ion to neutralize those aluminums. So that means that our formula becomes AlCl2, aluminum chloride. Again, we got zinc. I think we'll do a couple more. We'll finish this page and we'll take a quick break. Zinc, which is a +2, okay? And iodine, which, like the halogens, like the chloride, the bromine, all have a -1. So I need 2 iodides for every zinc +2. So our formula becomes zinc, ZnI2, or zinc iodide. Again, notice no prefixes, no Roman numerals, because every metal is part of the 16. We don't need Roman numerals, and we don't need prefixes. We don't use prefixes for ionic compounds. All right, now we have a variable oxidation state metal, specifically copper +2. Remember, that +2 belongs to the metal. That tells you what charge you're working with. That tells you that you are working with copper +2. That is what the Roman numeral represents. Okay, nothing else. That Roman numeral belongs to the metal. And then we know that the oxygen is a -2. Okay, so we can easily just put them together one by one, 1 to 1, because they're equal charges. So our formula becomes CuO. Now, if we were to name this compound, then definitely we would use the Roman numerals. It would be copper, Roman numeral 2, oxide. Okay, as compared to copper, Roman numeral 1, oxide. 2 different metals, 2 different properties. The metal 1 is an oxidation state of +2. The other example will be a +1. Okay. All right, let's do one more. And we have lead, Pb lead. What is the oxidation state of this lead? Pb Roman numeral 4. What is it?
Positive?
+4. This number, this Roman numeral tells you are working with Pb +4. Okay. And then the oxygens are the same, never changes. It's a -2. So I need 2 oxides for every lead +4. Okay, so its formula would be as follows. So, and its name would be lead. Okay, Roman numeral IV oxide. Okay, so let's, in fact, and let's go through all of them. Okay, we got the top one, which is sodium sulfide. Okay, and we have MgO, which is magnesium oxide. Then we have potassium phosphide. See the trend here where we got the sulfide, the oxide, the phosphide. We're dealing with the elements, the single elements all by themselves. Then we have calcium nitride, and then aluminum. Excuse my writing, you can't read it. The resolution of my pen is really digress. Chloride. Then we got zinc iodide. Okay, in none of these cases that we just wrote down, no Roman numerals, because the metals have exact oxidation state. Okay, and we did copper already, so it's copper Roman numeral 2 oxide and lead Roman numeral 4 oxide. Okay, and again, you mix and match. So sodium oxide, sodium phosphide, sodium nitride, sodium chloride, sodium iodide, and sodium, well, we did oxide. So you can do mix and match here, okay? But when you do mix and match, make sure you put enough of each so they cancel out. Enough of each of the cations and anions so they cancel each other out. All right, tell you what, I got 3 o'clock. Let's come back at 3:15-ish, okay? And we'll go from here. All right, polyatomic ions. We'll stop there. All right, we'll see you in about 15.